Uh-huh. Good evening, everybody. Andrea. I work with those two gentlemen, Jarmil and Puria, from Dyne.org. I will not show you Zenroom. I'm going to show you a very, very sexy PowerPoint about 6-7 slides that will introduce the work that Jarmil has been doing in the past couple of years on a subject that is very trendy nowadays. And as we started talking to skilled developers and informed people and blockchain experts, we realized that this topic is very often misunderstood, even though many people are curious about it. So I thought that I could introduce our zero knowledge proof cryptographic virtual machine by giving a little bit of information on what the zero knowledge proof is. So I put together a few slides called Zero Knowledge Proof Demystified. I hope you will enjoy it. And after, I'll pass the word to Jaromil, who's going to give a hands-on demonstration and give you a bit more info about the cryptography behind zero knowledge proof. Okay. Is there a mic that I can hold?
Yes.
Oh, much better.
Oh.
Yeah, perfect. Okay. Good evening. I'm going to start from scratch now. Good evening, everybody. Who has any idea of what zero knowledge proof is? Can you raise your hand? Anyone has working experience on zero knowledge proof? Okay, 1.5 person. All right. Yeah, okay, that doesn't count. That's cheating. Okay, let me get started. Let me see if I'm recording. Am I recording? I am recording, perfect. All right, so zero knowledge proof demystified. As we started working with zero knowledge proof and talking to clever people that have worked more than us with blockchain, with cryptography, we figure out that even though this word is in the mouth of everybody at the moment, there is a very little understanding of what it is and what it does. So I'm going to start what zero knowledge proof is not. So it is not a way to magically show information without showing it. Because that's what most people is assuming. They assume that zero knowledge proof means that I'm going to put my data somewhere, let's say my ID number, my birth date, my name, and my address somewhere. And that's not going to be shown, and then at some point is going to be shown magically. No, that's not what zero knowledge proof is. It would be nice, but we aren't there yet. Zero knowledge proof is not a crypto scheme to make information available only to selected people. That's also what is not. It is not a crypto scheme to share data without sharing it, because that's also something we heard. Because zero knowledge proof is connected with something called zk-SNARKS, which means offline zero knowledge proof. So people thought that you put some data offline somewhere and then magically they appear somewhere else on someone else's computer. No, that is we're not there yet. Very, very shortly, zero knowledge proof is a cryptography scheme to prove information without sharing the information. So what does it mean to prove information? It means that I want to prove a specific attribute about myself without giving out information that is not needed to share the specific attribute, or information that is more personal than the information I want to share. And by mentioning this, I actually jumped over to the next slide, because zero knowledge proof is often connected with ABC, or attribute-based credential, which involves sharing a specific attribute without sharing the actual information. And while going on, I'm going to show you individual cases of what zero knowledge proof could be used today. That would hopefully help you to better understand what kind of solution, what kind of problem this solution is trying to solve. So, case number 1. This is taken from one of the pilots we realized in the code, and I do see in the room the person that worked with it. So let's say that you are at a festival or at a bar and you want to buy a beer. And because of legal regulation, you have to prove that you are above 18 years old, but you don't feel like sharing your name. You don't feel like sharing your birthday. And on some ID cards or passports, there may even be your address. So you may not want to share all this information with the person that is checking that you are 18. So what do? You get a trusted issuer, something that in cryptography we call a credential issuer, to prove the fact, so to issue a statement that you at a certain date you are above 18 years old, and use this proof instead of your ID card to people who need to know that you are above 18 years old. So where this is getting us to? We are used to show our passports and ID cards in most situations. In many cases, this is not needed. In many cases, people just want to know that you're above 18. And zero-knowledge proof is exactly about this kind of situation. So you wanna be able to prove to the person in front of you a very, very specific attribute without giving up a wide amount of information. So this was case number 1. Case number 2, very similar. An individual wants to show that he or she lives in a certain area of a certain city because, for example, the person wants to use certain services from the municipality, or they want to have information about initiative. They want to have some commercial advertisement targeted, but they do not want to give up their address because they don't want to get spam. You could use the same. These two examples are very similar. They could be used to get a certificate about your health state. For example, if you have a certain health condition where you wanna share only some details about it, or you don't want to tell the whole story, but this health condition entitles you to get a certain product or service for free, you could get an issuer to state that at some point you're entitled to get that service without having to tell the whole world about your health condition. And health it can vary from country to country, but even within Europe, in some countries, specifically those countries who have a private or semi-private health system, health tends to be the most precious and the most confidential information we want to keep upon ourselves, because sharing that to the wrong corporation may result in having a significantly increased cost of living, a significantly increased cost of medical service and medication that you get. So that's something you really want to keep for yourself.
Andrea, may I say something?
Sure.
Fantastic presentation, but meanwhile he just disclosed that he lives in Österbro in Copenhagen, a gentrifying place thanks to him.
But you don't have my full address yet, so you cannot send me spam. We can work on that later. The third case is a little bit different, but this comes actually from real requests we have from real users. Let's say that in order to perform a certain financial transaction, you need to have a certain approval from your bank. And this approval usually requires that the bank checks your financial stability, that you have, no criminal records. They want to check your mortgage, they want to check your loan. Your salary, not your loan. And only after you have shared this information with them, you would be allowed to perform a transaction, let's say in a digital marketplace. This is also a very good use case for zero-knowledge proof, because you could get a certificate or a credential that is KYC based. KYC stands for Know Your Customers. That would specifically allow to do one type of transaction without giving up your data to the whole market. So you get a stamp where the bank digitally said this guy is allowed to do that without telling anybody else why you were allowed to do this. Okay, how does this work in practice? And this is my last slide for today. I'll have to pass the word to Jarmil. So the flow that we're going to show you is we can split it in 4 parts. In the very first part, and this is where most people get lost. No, sorry, the second part, most people get lost. No, sorry, it is the first part. Yeah, I can't remember my own presentation. Very, very often we are, when we talk about zero-knowledge proof and attribute-based credential, for example, in the DDDC pilots that we developed within the code, we have been asked how can an individual get from the same municipality a statement that the person is above 18, that lives in Barcelona, and is female, for example. One very common ground for misunderstanding is the fact that within the same certificate you could get those 3 informations. The way we'll solve this problem is that a trusted issuer, for example, the municipality of Barcelona, will generate as many key pairs, and we dig into that in a minute, 1 per attribute that has to be certified. So, 1 keeper can, for example, be called above 18. So, Barcelona's municipality above 18, 2019, for example. The next one can be called Barcelona municipality 2019, barrio, whatever. The third can be Barcelona municipality 2019, female. So the municipality will generate a bunch of keepers, and those keepers, the public key of those keepers will, well, a cryptographical object that contains the public key of this keeper will be published in a place that is trusted and is verifiable. Why is that? Because I could generate a key pair stating that I am the municipality of Barcelona, make a fake website called Barcelona with 3l.com and pretend I'm the municipality of Barcelona. That has to be avoided. So in order for zero-knowledge proof to be reliable, we need to make sure that the keys come from where we think they come. So publishing the keys is key. Sorry for the mess up. Publishing the keys is a crucial part in this process. One way to do it is publish on their own website in a way that it is provable without any doubt that they come from the issuer. A blockchain can work. A trusted API can work. Anyway, they have to be cryptographically verifiable. The third step includes the third step in when the user jump in. So the user will have their own key pair, and they will generate 1 request per attribute to the issuer. So the user will have typically a wallet where we'll send a request to the municipality, say, please state that I live in this quarter. This approval can happen by sending information throughout the network, or as we do in the DDDC pilot, as we do in the petition signature application, this happens as an offline approval. So someone physically walks in the office, one of the offices of the Barcelona municipality, show their ID, ask to get a credential signed, then the clerk sitting on the other side checks that the ID is valid, and then they push a button on the keyboard and they approve it and sign the credential, which gets sent back to the user. So this is those are the possible flows that can be known. When the credential has been signed, the user can use this credential in any situation when the credential is required to perform a certain operation. So once again, in the DDDC pilot that I believe you have seen a couple of hours ago, in order to sign a petition, you are required to have a certain credential. So that is the case when the citizen uses the credential to perform the petition signing, the petition signature. What happens at that point in the crypto scheme that Jarmil developed is that this credential, which by itself could be trackable if used on a blockchain, because the same credential can be used a number of times. So this credential becomes anonymized every time it's used. And this anonymized credential is matched to an object called verifier, which is a cryptographical object that contains the public key of the issuer. So you have a credential signed by the issuer on one side. Then you have another cryptographical object called verifier on one side. And if the two match, then the smart contract returns OK and performs the rest of the script. So this was how much I've been talking, like 15 minutes? So I wanted to do a little bit of talking before, because what we are showing next can be a bit hardcore for some people. So if I thought that if we show the theory before, the hands-on part would be easier for you to grasp. And at this time, I pass the mic to Jaromil.
Thank you.
Also, if you have questions at this moment, that's a good time to pose them.
Yeah, exactly.
Super fast.
Thank you. This is a sort of building a certification authority for each attribute a specific certification authority in which the citizen or the user can authenticate and get proofs or assertions, certificated assertions from, if I understand well. It's okay, or I missed some point?
It's a very plausible question. This is indeed one point where a lot of people get lost. So I'm going to answer you asking not to confuse a certification authority with a key pair. So the certification authority is one, and this certification authority can generate as many key pair as the certification authority wants. Each key pair will be used to certify a certain attribute. You could think that this is more cumbersome than having one signature, one certificate to certify many of them. But the beauty of our crypto scheme is that you're able to aggregate certificates into one single object. So in reality, what you get, what the credential issuer, so what the certification authority will publish, is a single JSON file that contains a very long list of cryptographical objects called verifier, which contain the public key. You're going to have one verifier for above 18, one verifier for that area. It can have 1,000. And it would be, I don't know, would be a couple megabytes with 1,000 objects.
So you can build also a taxonomy of verifiers, so of credentials, that can be summed, combined. And by knowing what is the result of the sum, you will know if this subject has that many credentials granted. And if you actually plan well the sums, you can have unique results for each sum. And you can combine. Technically, a verifier, so a public key of an issuer, is an elliptic curve of second order. What we call ECP2 is a twisted elliptic curve. So it's a double length than a elliptic curve point. Is the double of the length in terms of bytes, which ends up being quite large. So it's handy to have. Anyway, the sizes we are talking about, they are all less than RSA, than usual RSA. We're talking about the elliptic curve, then below the 1 kilobyte for such a key.
A little question about the trusted issuer key pair. There is a sort of relation between key pair, like the HT derivation of Bitcoin, like having a path of derivation, or not?
For the trusted key pair?
For every key pair that the trusted issuer generate, there is a sort of derivation path like the HT derivation of Bitcoin, or are simply multiple seeds and...
Yeah, multiple random seeds.
Yeah.
Why would you think it makes sense to have a derivation?
It's a counter question.
Yes.
Because if I try to envision how different cities and different countries use this approach. I like to have a sort of standards to the key pair derivation. So knowing the master of Barcelona, I can derivate the path for the age credential. Let me say. So for every city, I need to know only one master key. So there is only one master key to be safe and public verifiable and so on. And I can derivate every public key associated with it without knowing the secret, like we do in Bitcoin derivation.
Yeah, so far we did not need to derivate, but it wouldn't be too hard to implement, given that it's an established technique. I suspect that I don't know really which pilot would need it. In general, like zooming out in Decode, we have been very excited when we saw this technology really working and passing all the tests 1 year ago. Then we started saying, oh, let's implement this and that. And, I put in, if you look at the Git log, base 58, and now I'm looking at the new notation for the keys and compatibility with this and that. But being a project that is based on actual people empowerment, we needed to stop on technical innovation just because it's there and stick to the pilots. And so you will see many opportunities of development. They're not so difficult to develop given the approach, but we haven't explored all of them. So far, no one needed. One thing, for instance, that we did by mistake is implement threshold verification, threshold verifiers. So with a simple Lagrange interpolation on the aggregation of the public keys, you can actually have a quorum of keys needed to verify. So 5 signatures out of 8 are enough. And we thought this would be really important because if a server from a city and from the Decidim and from the region is down, 2 will be still enough to verify it. But no pilot on the interviews has actually expressed that concern. They just trust one thing. So we have that, almost ready, but we did not deploy it.
Are you recording?
Yes.
Are you sure?
I'm.
Okay, we're sure.
Yeah.
What about attributes that you do not want anymore?
Great question. So we also did not have that expressed by pilots yet, but by one brilliant new pilot that joined us, Alex Puig, that you just saw presenting before us. He started posing the question of revocation. We are researching it. Main reference is what Indy is doing in Hyperledger. But we believe we can have an even simpler solution for that, and it's based on the Z cofactor that we use in the petition to make sure that the vote is unique. So we will do a sort of revocation table of Z cofactors and use that as a broadcasting revocation tables.
Yeah, but it's not a matter just of revocation. It's a matter of deleting some attributes, something that I do not want anymore. If you store them on a blockchain, if there is a link on a blockchain that states that something was related to me or to something else in a blockchain, they will still forever.
Yeah, that's
and
what we
if
call.
Maybe I can answer. So I think that you're asking. So that your question, when we talk about revocation, usually the point of view is not the one of the user, but is the one of the network that has to blue stamp the output of the smart contract. So usual revocation is about this guy, this user was allowed to do this, now it is not allowed anymore. How do we prevent him or her to perform the operation further? This is usually the question about revocation. But I believe that you're asking how, if I have put some of my data into a blockchain, how do I get it deleted? If some of my attributes are somewhere...
If I had once the authorization to do something because I was a female, and now I am a male, and I do not want that someone discover that once I made something because I was a male. You cannot delete anymore this information from the blockchain.
I closed my computer now.
Well, the indie paper has a solution for this.
Okay, hold on. There was a very short step that I didn't go deeper into because he's going to do it now, about how a credential is used. So let's say that you get 3 credentials. One is I have glasses, one is I'm above 18, and one is I'm male. And those 3 credentials allow you to get cheaper glasses, get male underwear, and get beer. Let's say you don't want the... Okay, this is what you get, and a few times you buy beer on the internet, okay? Let's say you want to buy 3 times beer on the internet or using a blockchain. The way we solve this problem is that every time you use your credential, this credential is going to be anonymized. So if you use the credential 3 times, the digital track you leave on the blockchain are 3 different objects that cannot be traced back to you. So this is basically you asked to solve a problem that we don't have, because by design we are not leaving trace of credentials. We are only used anonymized version of each credential, where every time the credential is anonymized differently.
He's right, yes, and he got the... Sorry, I confused, thanks Andrea, because I was talking about revocation of issuers.
Please go with the hands-on.
Hands-on.
Yeah.
Hands-on. Yes. But very interesting questions, so it shows that there are some people we want to talk to after this demonstration. So, hands-on as much as I can. Let's see. How looks like a Zen code. So this is one that I particularly like. It doesn't do exactly what we talked about, but it shows you that you can do simple things with. So that's we version the rule. So that's a code already. We call the scenario. Scenario simple is the default scenario. And after the colon, you can have any sentence that helps you remind what you are doing. Grazie, Puria. Yes. Human technology. Human touch. Indeed. So, this is where the code starts. And as you see, the code starts with given nothing, because the 3 parts are about read, write, and write. And if you want to make sure that your virtual machine is running with no input, you can do that too. You say given nothing. In that case, Zenroom will give you an error if there is anything in the input data. Then you say, I create an array of 32 random objects of 256 bits. As you see, there are numbers between single quotes. These are variables. You can insert your variables into your sentence. They could be other numbers. And then as a third part, you then print the array. Where this array comes from is here. Every time you say create you are creating a new variable that you can actually refer to in the then section. So I press enter, and here I have a list of highly random 32 objects in base 64 URL notation. So what do I do with them? For instance, I could generate random URLs for secret things that people want to download online, or things that only the people that I give this URL will see. And it's very simple. So if you want to do this in your Python program, in your Go program, anywhere in any language, you just embed the Zenroom, you pass it this text, and it will give back this JSON array. It will also give back versioning, so that in case in the future we break something, you can always check. It has also functions to automatically check. So that's a little bit like it works, the Zen code, the language. I save you the implementation details of how it fits in 2 megabytes. I'll have a lot to say otherwise, but I want to concentrate now on the language, because that's, I think, the entry point for someone that wants to use it. So this is an attempt at a cheat sheet that I think should describe all the language. It's not a very complex language. And this cheat sheet shows you the language on the 3 parts of the heap, the memory. And for purely Scheiniger reasons, I will use a fork to point at these parts. So you have the upper part. Thank you, Purya. You have the upper part where steps, memory, instructions. You have 3 columns here, and you have 2 rows. Okay? And the code executes from up to down. The first part starts with given, and any part can be reiterated with and. So I can say, given I am Alice, and I have a valid public key inside Bob. So it means that at the entry there will be a JSON structure with Bob, and inside there will be a public key. And if I use valid, there is a schema validation. So before proceeding to the next instruction, Zenroom will actually check that that public key is an actual point on the elliptic curve that is configured. So that's a semantic check. And that is security. So you don't accept just any string, you just check that it's an actual curve point. So given I am Alice and I have a valid public key inside Bob, when I use the public key of Bob to, I will show you the when part. It's not written here, but it's the custom part. So I use the key of Bob to sign my message, and I draft a message with written hi Bob. Then print all or my message, encrypted message, as base 64 inside something or not. What does it mean? That the my, what I should specify, it prints out the result. What I should specify is that in the my, it means that at the entry and at the end, if you declare yourself as being Alice, this will always be taken from and put into a substructure called Alice. Why? This way you can really easily express what is regarding my own keyring, for instance, and someone else's things. So you can split it at the end. You can also say, then print only my private key, and then print all Bob's keys. But then you declare already, I'm Alice, so I don't need to say who I am. I'll go a little bit further. This is a list of typical then things implemented. There are not many. And with this, we do most of the stuff that we need. This is the generic when, that's not scenario dependent. So you can say, you create a random, you have seen, I set message to hi Bob. I set message as base 64 with hi Bob. Or you can append. So, and then you see, and I append, and I append. And you start creating into the memory a data structure. And the given is also pretty simple. I have a valid inside, valid from, and so on and so forth. So that's most of the stuff that you need to know to write a normal, simple contract. Then it comes the scenario. So let me go up to a simple scenario. Yes? Signature, public key signature. A public key signature this is a simple DSA. So you sign a message that's in clear. That's not going to be hidden. It's ECDSA, what we are looking at. And we have Alice with a key pair already created. So Alice will say, I'm known as Alice, and I have my valid key pair. Valid means schema validation. You don't have a valid key pair, it has been tampered with, one bit that is different, it will return error and say, error on valid key pair. So you know exactly where it is, which is a huge problem. If you have ever developed, you know how many things can move wrong, and you need to have clear errors. Then I create the signature of draft, which is maybe another JSON, another JSON part that is called draft. Then from here on, you know that since you said I create you will have an object called signature. And then you say I verify the draft is signed by Alice. That's the flow. Sign the message, sign the message, prepare the keyring, verify the signature by Alice. Why this is cool? It's because this is apparently simple, but you have to distribute this computation on several moments and sometimes on several devices. And what happens is that you have a server maybe, you have a mobile phone, and you have a browser. And these operations need to happen in different points on all these devices. Andrea has written a very interesting blog post on the Decode blog that you can find about determinism and why it's so important for us. We need to be sure that the same computation will actually yield the same results across all these different platforms. And we had a huge problem that took us a week to solve. It was a bug in Python. Dare to comment about that?
Maybe it was a feature, not a bug.
Yeah, there was a recent article also on the Invented UK. Our problem was not exactly the same problem, but was related, and it was, we don't want to blame Python language for this. It's a very cool language, but if you want like pure determinism, you have a lot of variables.
Yeah, I can, in 5 seconds, we were hashing a list of emails. I think it was SHA 256 or something. Yeah. We were hashing a list of emails in Python 2. And then matching this hash list on a service running on Python 3, and the two lists didn't match. So the same algorithm, Python 2 versus Python 3, did not yield the same result.
So, oh yes, I can do this too. So I like to show you tests. One thing that we solved is that in Zenroom we have the tests constitute the documentation. Okay, don't mind the red stuff. I don't know how to switch it off, Puria. This is Vim.
ZZ.
Oh.
Or ask column Q.
No, I mean to remove the red on the right side.
Column set no list. Is that one?
No list.
Okay. No, you removed already.
No, it's
No, the
yeah.
You're highlighting.
Okay,
No,
never mind.
run it with Vim and not with VI.
No. Okay. Not so important. No. So what you see here is how we prototype things. And this script has a lot of comments, and some of the comments are actually Greek symbols because you will find them in the coconut mathematical formulation on the paper. So we really like to document the passages from a mathematical formula to what we do. And here you see lines in which we launched Zenroom on files. So when we prototype encryption flows, we write each of these statements, then we take the
output, then we feed it into a new iteration. And we make it, this is a simple shell script. And every time we run it, it just runs through all the phases and tests that what we expected is exactly what it is. It's very simple this way to write both the test units and the documentation. Actually, the Zen files that you see here, they are the same that you see on the web page because they compile into the web page and we show them. So if we change something, it stays consistent. Because it is an amount of information that is quite big and it becomes really hard to deal with. So here you have the petition flow. This way also becomes very clear the question that was in the air a lot of times when we interacted and also in the talks is what do we put on the blockchain? What do you need to put on the blockchain? And you really need to visualize the fact that you put on the blockchain only what is not referable to anyone because it's complete public space. It can be also something encrypted, but if this encrypted thing is the same every time you show it, I can trace you. That's where I can trace you. So it needs to... This is back to the question. So I think I'm trying to follow your curiosity. There is so much to talk about. But one thing is actually here in the credential, attribute-based credential, and you see it here, exactly. So this is an important part. This is when someone creates a request for a credential. This is a channel. It has to be rather secure, but it doesn't need to be super secure. This channel is traceable. So I can trace the requests, and that cryptographically I cannot avoid it. This is the part where we sign. So we have a request, arrives, the issuer decides that it can be signed, takes her own issuer keeper, produces the signature, and gives it back to the holder. At that point, the holder has a signed credential that can be shown as Andrea described. Now, this passage here is the credential, and if Alice would show always this credential, she could be tracked. That's why Alice does a proof. And this proof, since we use Elgamal, the Elgamal crypto system underneath, actually has a cofactor that randomizes it every time we show it. So this proof can be on the blockchain. This is the blockchain space. The blockchain space will have the public key of the issuer and the proof, which will be always different, so I cannot track this person. This is the underlying crypto of most of the blockchain stuff that you see around on the ZKP. And anyone, we can trust anyone, or it can be trustless, can check that the verifier is actually matching the proof. So you broadcast it to the blockchain and you say, hey, I'm Alice and I'm lost in Wonderland. And this is the verifier, which is the public key of the Mad Hatter who signed my declaration. And anyone can actually verify this. So you broadcast it, you receive 6 confirmations, and then a transaction is done. That's how Bitcoin does it. This is the sequence diagram for this. So in time, from top to down. It's not really rocket science if you start getting into it, and you can do a lot of fun stuff. If you consider that inside the credential in Coconut for the petition, we put homomorphic encryption. Which is very possible on integers. Homomorphic encryption is a Graal, some of you heard it about, is the technology that will make you search into a database without actually seeing what is in the database. But that's very hard because on strings it's very hard, but this is on integers. So why we need it is because legally in a petition you should not know the current sum, the final sum, You should not know who has voted and if, and no one should know the result until the result is tallied. Luca. Aspetta il microfono perché stiamo registrando tutto.
Yeah, I was considering that in the W3C model for verifiable credential, they in fact always manage credential exchange and proofs of ledger. Is there any reason why you choose to write proof on the ledger? Or is this because of some specific requirement?
The only use case that needs the ledger so far is the petition system. And actually, it's not that necessary. And I'm scrolling down because it's very interesting. What I just showed you in all the steps is all these Zen codes do all the steps that I say. You can see it on the website. But if you don't need a distributed credential issuer, the power of the language Zen code allows you to just condense everything in one sentence, and this will actually generate and give you a new credential without you requesting it. Because as an issuer, I will generate it and give it to you if you trust me. So you can actually combine all the steps and compute them on a single machine or distribute it. Same concept. You can have a ledger if you really distribute all the steps and you have certain points of trust. To answer your question, one needs a specific pilot case and an analysis, a design session that we usually do. It lasts 1-2 days, and we nail down the problem. We have a set of contracts like this, and then we implement it. So just to give you an idea, with Zenroom, we can do also an ad hoc cryptographic system for something, keeping everything intact underneath, modeling of 2 days, and in 1 week we have the product. There is even more space for customization. There is an underlying Lua language that you can access immediately, but the Lua language is not safe to, is not untrusted. So we have removed most of the dangerous functions from it, but one can still crash the machine or put it in an infinite loop. That's why we use Zen code, because we want to accept untrusted code. And if you use Lua, you need to know what you're doing. And in Lua, you have all sorts of things, and they are all well documented.
We have less than 10 minutes left, so maybe we can show the audience how to do an offline zero-knowledge proof flow, where you do some part of the flow on the web-based version of Zenroom, and the rest on the command line native version of Zenroom. That would take 3 to 4 minutes. That's what it takes to me. Let's see how long
Let's see if I can do it.
Exactly.
Okay. Ansia. Okay. What are we talking about?
Hold on.
This wasn't prepared.
I don't think that wasn't prepared. I don't think we mentioned it, but the tool we'll be talking about this whole time is written in C, so NCC99, which means it can be compiled and run on pretty much any platform that you can think of. And as well, it can be compiled into WASM and run in the browser using WebAssembly. So we can do half of the cryptography inside the browser, the other half on a command line application, and redo exactly the same cryptography in an app. And on a Linux server, on a Windows server, or a Mac OS X computer. So yeah.
I'm an Emacs user.
Ah.
You have Emacs? Oh. Emacs takes time to start. Okay, test Zen. I'm copying here I'm copying the rule that is online. This is online, the demo, and I'm taking this is not a zero knowledge proof. I'm taking the decryption the encryption and decryption, because then it's only one passage. But the one on the terminal is also there in the tests. So I run this completely in the browser, and this is the data and the keys. I need to be sure. Well, let me reload. So it's all clean. I encrypt this message, which is, okay, this is the public key of Alice, and I think the data is here. No, this is the Bob public key, scenario simple, encoding, and that's the message. Okay, well, I will press run, and this produces the secret message. We don't know it because it's encoded in base 64, so we need to decode it in order to know it. This is the contract I'm using. Okay? This is the contract I will be using to decrypt it, which is readable there. All right. So then I put it in how did I call it? Test Zen. Yeah. And Zenroom is in the path, so I do test Zen. And of course I have a syntax error because I don't have the input. You have the latest installed? No.
I think it's a compiled one.
Here you have the latest, yes. So just make sure that the version is the same, and then I do a test Zen. Okay? Syntax error nearby check. I sort of delete this. We really did not prepare this, but it's fun. Yeah. And I need to execute it, of course, with -z. Okay. Look, I executed the code, and Zenroom is telling me, okay, it's missing a version. First of all, you should version your script. I just deleted the versioning. It's saying, I have my valid key pair. There is an error there. And I cannot find a key pair inside Bob, because I just launched Zenroom without an input, without the input that I should give in. So cannot find key pair inside Bob. And then it dumps the heap. It means it dumps the memory state. And this you can get also in JSON inside your program. So actually you can transparently print this out in your application. And it says, yeah, I know that you're Bob because I processed this. But at the key pair I got an error. Okay, so let's see. I like these challenges. I'm sweating a little bit. This is the second script with the keys. Yes, this is decrypt. Yeah. So I get the secret message. As keys, I give them my keys. Okay. So test data. Oops, again. Where is Emacs? Did I close Emacs? No, it's not my desktop, so. Dov'è Emacs? Alt tab?
And that works. Now you close it.
If I do it with my computer, maybe I was faster. Sorry. Test data. Okay, I put it here. This is the secret message text. Okay. I close it, and then I put the keys. The keys. This is the data, these are the keys, okay? Control A, Control C. Then test keys. Uh-oh. We have different, that's the beauty of having different desktops.
1 minute to go.
Fuck. Test keys. Ooh. The copy. Okay. I will fail this, I think. No, that's the keys. Okay. If it was on my desktop, I was done already. But you need to adapt. Yeah, I just brag about. Okay, so.
Now going to the other one.
Test. Then. No, I need. Source, Zenroom, -z, test, then -a, test data, -key, test keys. Boom. I got it. The message is, this is my secret message. It was decoded.
Okay. Before you clap your hands, I need to remind Jaromil that the name of this workshop. Yeah. We got it. The name of this workshop was how to do an offline zero-knowledge proof flow with Zenroom. So if we don't show that, people are gonna ask for their money back. That's gonna be an issue. But still,
No.
some people
this was
will still
funded
claim
with
their-
tax-paying money.
Exactly. So someone from the commission is going to ask for their money back. And this is going to be an issue. So I think that showing the full flow is going to take some time. But at least show which contracts are used, what contract does what. So
Yeah, that is the same contract with the same input running into the browser, and as you see here, there is the same result. The header has a checksum and all that. Another example, very quickly, of in-browser is the web encryption demonstration.
no,
which
we have to run. We have no time.
it may interest many of you. This is a very simple contract to encrypt a file before uploading it. So you want to do a file upload, you load the key, this is the code, and here you can choose a file from Puria's private stuff. Miniconda.
No, that is so big.
No, it's a shell script.
No, I'm telling you.
File size system. Yeah, è il tuo computer del resto. Infatti sì. Okay. And I did upload file because it's like the default way to call it, but this has not uploaded. This has encrypted the file. I can take this as JSON and then upload it. And one thing that I like to show you is how simple for the coders in the room is the shell script for this. This is JavaScript. Public domain, if you use this, you just use it. And yeah, you see we put inside the JavaScript the contracts, setup form, upload, almost over, over. And this means that you can embed it into your JavaScript before uploading, and so on and so forth, request stuff, and so on and so forth.
Thank you very much.
Sorry, now it's a real time to show how to do a zero-knowledge proof within Zenroom.
No,
Which no, it's not over. I'm overruling the time.
No, you can't, because we have a presentation after.
No. We have our friends from VAG, but I'm sure they will indulge 5 minutes longer.
Okay.
So just so that everybody, so one of the main purposes of this workshops is that it will be recorded.
I don't know how to behave.
Is just smile and turn around.
Just remind me, it's recording.
Yes, it is recording.
So I need to keep on this desktop.
Yes,
Because
but just show the contracts used. Just a very quick how-to, so that people that watch this video can play with it at home.
Okay, you download Zenroom. That's the source code of Zenroom. You go in test. You go in Zencode Coconut, and well, this is it was already run. If it's the first time you run run petition example, actually the first is run Coconut example, is a shell script, and it will run and generate one by one all these scripts. So it will execute credential keygen, and it will print out the result into a file. Then the file will be called by credential request with key pair keys. That will be the file. It prints out another file. All these steps are repeated one by one, and anytime you can look at scripts, which is this list of scripts. They are the .zen, and you can look at the JSON files, which are the results of this creation. And anytime you can go inside one of them and see really what is inside. The credentials that I showed, mutating proof, is in here. So maybe you have JSON PP? Oh yes, fantastic. So just for the sake of clarity, I love that you have US keyboard. It's like I really need that, otherwise I was failing. Yeah, these are the credentials. And anytime you can look into these files, it becomes quite manageable. This is the tally of a petition if you run the other script. It's a little bit bigger. The homomorphic encryption is fencing the vote to 1, so we use a system of positive, negative scores to check that the vote is only 1, and so on and so forth. You can see.
Okay, I think that the very last thing is that you want to show the shell script.
Yeah.
The shell script.
Yes.
So Zencode.
No, Coconut example.
Coconut example. This for the.
So here you have the whole zero-knowledge proof flow with all the steps from the generation of the keys of the credential issuer, the generation of the keys of the users, the generation of all the crypto objects that are in between, to the proof that the credential, the anonymized credential matches the key of the issuer. So you could basically, if you need to have a zero-knowledge proof flow with, let's say, 10 different attributes, you could modify the script to run it 10 times, one per name of the attribute, and you would have a credential issuer. You would have all the cryptographic objects you need to run a credential issuer with 10 different attributes. So we spoke 1 hour to show this one script of 20 lines.
So, and since we have the opportunity to have Mike Scott in the room, I would like to thank you for the fantastic Milagro library, because that's the underlying crypto arithmetics that we have in Zenroom, and it's super fast, as you could see. Some of these operations take a long time to go. So, thanks, Mike.